without further ado, I want to quickly introduce Bolei. He, speaking of MIT, he recently just graduated from MIT in Antonio Torralba's lab. Congratulations to that. So it's nice. And he's currently a postdoc there, and I think you can tell more about yourself if you want to. Otherwise, it's also nice to just go into the topic. Thanks for coming along. And
just 10 minutes walk, not coming.
Oh yeah, that's actually true. It's not too far.
Very happy to be here to see such a large machine learning community. So I just graduated with my PhD degrees. So my research interest is on computer vision and machine learning. So specifically, I'm working on visual scene understanding, like taking a photo to recognize what a scene category it is. So another research interest is on interpreting the machine learning models. So after you train this machine learning models on millions of data, so I try to understand what's going on here. So I would like to start my talk with two questions. So the first question is, how many of you make a living by training machine learning models? Okay, about 2/3. So how many of you are make a living by training deep learning models? Okay, still we have 50%. That's great. So I hope after the talk you can have a different thoughts on the models you are training, and not just monitor the validation nodes, but you can, out of curiosity, and take a look what have been learned inside. So today my talk is about interpreting representation for visual intelligence. So as you know, deep neural network is widely used for visual intelligence. So for example, the neural network understanding the visual scenes, so giving an input image, the network can tell you what are the regions for the person, and the region for the car, and for roads, so that autonomous driving cars can navigate through the environment. Also, neural networks are making medical decisions. So after you're training millions of medical images, the network can tell you whether you have tumor or not. Also, neural networks are playing the Go, such as AlphaGo from DeepMind, that already outperform our best human players. So because I'm a computer vision researcher, so one of the milestones in computer vision is a large-scale data set, such as ImageNet. So ImageNet has 1.2 million images from 1,000 categories. So before deep learning, people try different traditional machine learning models, so just to get so-so performers. But after 2012, people start using deep learning models, then the state-of-the-art performance for object classification keep increase. So from 2012, AlexNet is proposed with 5 convolution layers. So you get pretty impressive performance at 84% accuracy on ImageNet. So 2 years later, then people propose VGG with 16 convolution layers, improve the performance. Then people propose a GoogleNet with 22 layers. Then people even use much deeper networks, such as residual network, which has more than 100 layers. So people propose different network architectures to boost the performance. So in terms of the top 5 performers on ImageNet, so you can see over the years, people use deeper and deeper network to improve the performance. So it's improved to 95%, is even outperform human players, human object recognitions. However, the final output is just one part of story. Another part of story are the internal representations. So here you can see giving so many layers and so many units. So what are they doing? So here are the 3 questions that I'm pursuing over the years. The first one is what have been learned inside those different networks. The second question is how to interpret the internal representations. The third one is after the network gives you some predictions, so why does the network give you such prediction? So I will try to address those 3 questions during the talk. So previously, the neural network is considered as a black box. So giving an input, the network doing some magical work, then give you pretty accurate human level recognition, give you the output. So the interpretability of deep neural networks is not so obvious. However, the interpretability is relevant to a lot of critical applications. For example, it's relevant to the safety of AI models. So when we deploy the deep learning models for autonomous driving scenarios of course, we want to make sure the AI model is doing reasonable things. So we don't want the Uber accident to happen again. So we want to make sure the network is understandable and interpretable to human beings. Another topic is relevant to the trust of AI decisions. Let's say the AI models tell you have cancer. So how much confidence you can put on the AI models? Why this network give you such predictions? So it's also relevant to the policy and the regulations. For example, 2 months ago, the European Union issued this GDPR regulation that, so one item in the regulation is that the common people have the right to the explanations for algorithmic decisions. So basically for any algorithmic decision predictions, the models need to provide some explanations why this give the predictions. So if you cannot give reasonable prediction, you cannot deploy the systems in a common scenario. So also the interpretability of deep neural network is a controversial topic. For example, last year at NIPS, so during the test of time award talk, so Rani Rahimi criticized that current machine learning become alchemy. So he said alchemy is good, alchemy works, but alchemy lacks the rigorous proof and justification why they work. So so whenever there's some controversy, there's someone will jump out and post something. So Yannick Kun tweets back. He said the alchemy saying from Ali Rahimi is wrong, so it's insulting. So you can see there's some controversy going on there. Also, there's another scenario at the NIPS last year. It's an interpretable machine learning scenario. There is a debate session on if the interpretability is necessary. So on the four sides, there is Rich Carolla and Patrick Simot, who are senior researcher from Microsoft Research. As a guest side, the Killian Weinberg, who is the professor at Cornell, and of course Yannick Kun is the guest side. So it's a very interesting debate. So if you have time, so I will suggest you go through the debates. So in this debate, Yannick Kun gave a pretty nice analogy. He's saying when people drive a car or use a TV, you don't have to understand what's going on there. But I'm saying if the car broken or TV broken, there needs someone to fix them. So they need to understand what's going on there. So for me, I think the interpretability is very important. It's a very important topic. So if we want to understand the neural network, there are several different granularities, different levels. So here is the standard plot of the convolution neural network, commonly used in computer vision. So giving an input image, there are several layers of convolution. So each layer, there are many convolution filters. So here I call each convolution filters as units. So each unit are doing convolution. That's crystal clear. But since getting massive when we train this network on millions of training samples, so it's getting hard to understand why this network gives you such prediction. For example, giving this input image, give you this cafeteria. So why is that? So to understand the network in several levels, so one level is that we can understand the network as a whole. So people propose different network architectures that try to address the overfittings because they want to improve the performance on the validation set. So you get better performers. Also, people try to analyze the features. So how those different features can be generalized to new scenarios, such as you train the network to recognize the object, how those features can be reused to recognize different cars or different scene categories. So people try to visualize the features to see they are discriminative and they can differentiate different categories. Also, we can understand the network at a fine-grained level, at the individual unit level. So try to understand what each individual convolution filters are doing and what they have been learning through the training process. So here I will focus on the fine-grained part, try to understand the individual units in the following slides. So here is the agenda. So I'll give you some introduction about my previous work on interpreting the internal representations to try to understand what those individual units doing inside the network. So second half is I will talk about how can we build explanations for the prediction given by the network. So all the papers or the source code are on my homepage. So if you are interested after the talk, so you can go there and download them and play with them. So previously I already showed you that people in computer vision working on the object classification, they build pretty nice network to achieve the human level recognition. So they can recognize those different objects inside the image. So this is a discrete object in each image. However, in real scenario, we are actually inside a scene environment. So in this kitchen scene, there are actually different objects. They have such special configuration, they jointly form the whole things. So if you really want to build visual recognition system that can scale up to real scenario, we need to work towards scene understanding. So before that, there is no large-scale data sets that can train network from scratch for scene recognition. Therefore, we built this Placeit database. So this Placeit database is the largest scene recognition database so far. So it contains 10 million images from 400 scene categories. So here I show you some image samples from the bedroom categories. So we have the spare bedroom, messy bedroom, teenager bedroom, romantic bedroom. So you can see all the different kind of image samples from the bedroom categories. So hopefully if we train the network on such diverse samples, we can recognize the real scenario of the bedroom. So after we collect such a large scale data set, of course, we train some deep learning models. So based on the model we trained, so I built a scene recognition demo. So basically it's a web demo, so you can take a photo and upload to our servers, and this network will return the predictions. Like for this particular image, the prediction is comes through. This is actually John Smith from IBM, who fellow in. So he came to MIT and gave a talk. So I took a photo there. So here another photo. So this so I went to Hawaii last year. So I took this photo when driving. So it's not a good activity to do. So for this particular image, the predict that's highway. So make the wrong prediction if not highway. But the second prediction is car interior. So amazing that standard work is aware that I'm inside a car. The third prediction is also correct. It's field road. So here I try to test this system. So I upload some oil painting. So I upload this oil painting. This network still give me the pretty reasonable prediction, predicted as cultivated fields. It's such amazing predictions. Yeah. Some questions?
Should I ask a question now or at the end?
Yeah, sure. Feel free to ask.
So you don't add up to 100%. What were the other predictions? Like of your conference room, that's 45%, right? So 55%. The majority believes it's something that's not a conference room. What do they think it is?
Yeah, those are the top. Those are the sorted predictions. So we only plot the top prediction, which are higher than 0.3.
Oh, thank you.
They are top 3 predictions.
Thank you.
Yeah.
Thank you.
Seems to work.
Yeah, it works.
You did your camera on.
Oh.
So demo works.
Yeah, you can take a photo and give you the prediction. It works, right? Predict the lecture room, right?
Yeah, it gets for a photo of you. It gets indoor.
No, you're going now.
Lecture room, classroom, conference center.
Yeah.
Enclosed area, no horizon.
Yeah, so give you the prediction on some scene attribute, also give you the prediction scene categories.
So for the middle picture, I mean, it's not wrong for any of those things. I mean, it's a picture of all of those things, but how you would categorize that is sort of a different question than what's in the picture. So I was wondering how you
For scene recognition is a little bit ambiguous compared to object recognition, because seeing that all different scene components and jointly forming the whole thing. Yeah, but I will see the majority of what's the majority part of the image and belong to the categories. Yeah. So right now we have 2 networks. So one network is a network trained on object classification. Another network is trained on places for scene recognition. Right now I use the same architecture. So the only difference is that the input data is different. So one is the training data is the image land, another one is on places. Right now, this network gives us the chance to see what have been learned inside this different network. So how these representations varies across different data sources. So the first thing we can try is to visualize the internal unit. So here I use a data-driven way to visualize the network. So basically, we can prepare hold out images, which have, let's see, 10,000 images, and we feed those images into the network. Then we record the activation for each one of the image for each one of the units. Then we can simply rank the units, or simply rank all the images by the unit activation and get the top activated images for each one of the units. So here, let's say we want to visualize 3 units as a layer 5. So get the image and sort the images by their unit activation. So here are the top activated images for unit 1. So you can see this unit seems respond to the lamp. So because for each one of the image, it will generate a special feature map. Then we can further binarize the feature map, then upsample the feature map to the original image, then segment the whole image. So this gives us such segmentation. So this image segmentation will highlight which region is the most frequent regions by the unit. So this is particular unit. This unit really like the lamp. So I can do the similar things for all the different units. So here are the top activated images for the unit 2. So this is activated by the face. So you can another activate by the trademarks. So to visualize networks, there are a lot of previous work. For example, the deconvolution is a way to visualize internal units. So they show that the unit at the lower layer, such as layer 2, are detecting texture or surface. The unit at the higher layer, such as layer 5, are detecting more semantic or meaningful concepts, such as a dog head or bicycle wheels. So backpropagation is also a common way to visualize internal weights. So basically, you use gradients to modify the input image, then they can back project the knowledge into the image space and see what have been learned inside. Also, the image synthesizer is a way to visualize the units. So basically, they train some generative models that can generate the image and maximize the activation of some individual units. So all those visualization methods are pretty good. They give you the intuition, what have been learned inside. But one drawback for the visualization is that they are qualitative. So you always can do some cherry picking to pick up some good visualization and ignore all the rest. So ideally, we want to move from those qualitative visualization to quantitative interpretations. So how can we get interpretation for all the units? So the first thing I try is to manually annotate all the units. It's how we manually annotate all those 10 million images. So basically, we can send the top activated images to Amazon Mechanical Turk, which is a crowdsourcing platform. So we pay the workers to come up with some description to summarize top activated images. Then we further ask them to cross out the outliers. Then ask them to classify the description into one of the 6 meta classes. We can analyze the statistic and how the statistic change over the layers. So here is some results. So we annotate all the units at common 5 layers of AlexNet trained on ImageNet. So here is the histogram of the object detectors annotated. So you can say most frequent detector is actually dog detector. So why is that? Because out of the 1,000 ImageNet categories, there are about 200 dog categories. It's more like people spend so much effort to train a network, but it turns out you get a dog specialist. So we do the similar annotations for the object at common 5 layers of AlexNet trained on places. So here's a histogram. So you can see the most frequent detector is a building detector, then the tree, grass, floor, mountains. So from the comparison of the histogram, so you can see the network trained on 2 different sources, built completely different set of vocabulary to represent the input data. So really the representation change depends on the data, how your data, the data sets, and how they represent the input data. So previous work is on interpreting the AlexNet, which is already 5 years old. So there are only 1,000 units, then we can manually annotate them. Right now, people use much deeper networks such as RedNet, DenseNet, which has 100 layers, so more than 100,000 units. Yeah.
Question. For the Mechanical Turks, how consistent were the classifications that were?
So for each unit, we repeat the annotation 3 times. Then at least 2 of them match the same words, then we consider these are reliable detectors. So about 1/3 of units are reliable detectors.
1/3.
Yeah.
These units that you're showing us activations for are all from convolutional layer 5, right?
Yeah.
Why is convolutional layer 5 most interpretable? And is there any layers beyond after that provide?
Yeah, that's
that's
a very good question. So in the paper, we actually analyze all the layers. So it just turns out the Quantify layer is the last convolution layer, is the closest layer to the final predictions. So you can see the previous layer maybe just build some components, then build a component and use fit the component for the final predictions. So closer to the final prediction, the more semantic it is. So from our analysis. So right now we want to scale up the interpretation to deeper networks, such as a network with 100 layers. So definitely we cannot manually annotate them. So last year, CVPR, we proposed a technique called network dissection. So network dissection is a toolkit to quantify the interpretability of network. So basically, you can fit any network insights. The network dissection will help you identify the interpretable units, also evaluates the interpretability of the whole network. So it's an automatic method to identify the interpretable units inside the network. So how it works? So the idea is actually pretty simple. We just evaluate the unit for semantic segmentation. So rather than annotate each individual unit, we first annotate testing data sets. So the data set contains 60,000 images annotated with 1,200 concepts. So right now we can generate the top activity images. And on this testing data set, let's see here are the top activity images for unit 1. So we generate the segmentation. Because for each one of the testing images, we have the pixel-wise annotation, which means for each one of the pixel, we know what's the semantic category for the pixels. Right? There's a purple region is a bad region, and those gray region is a wall, and the lamp is the yellow regions. So we have such annotations. Now we can simply use a feature map to segment the annotation mask. Right now, we can simply count how many ground truth pixels have been segmented by each one of the units. Then we can sort them and associate the top concepts as an interpretation for that unit. So for this particular unit, the top concept is lamp. Here we use intersection over union to measure the semantic segmentation accuracy. So basically, we take the overlap region of the detected region and the ground truth region and divide by the union of the two regions. So this IOU gives us a number to measure how accurate some concept is aligned with the unit activation. So here we define the interpretability of units as a degree of alignment between the concept and ground truth in our dictionary. So here is a histogram of the unit identify the network dissection. So at the Quantify layers trained on places, so out of the 256 units, there are more than 100 units covering 72 unique concepts. So we have 32 object detectors and some scene detectors, materials detector, and texture detectors. So here is one unit 79. The interpretation given by this method is a car. So it's car detectors and detecting the car with IOU at 0.13. So here's another rope detector. So unit 107 and detecting the rope with the IOU at 0.15. So here you can see the IOU is relatively low compared to the supervised trained object detector. But I should emphasize that when we train this network, we just train the network for scene classification. We don't give in any object supervisions. It's more like those are emergent detectors. They emerge inside the network without explicit supervisions on objects. It's also relevant how humans do scene recognition. You will see that people and chairs inside this lecture room. So the network is doing similar things. Try to discover the most informative object before it classifies this whole image into some categories.
So doesn't the value of the IOU depend then on the threshold that you set for measuring if the feature map activates or not?
Yes, depends on the threshold we set.
So what threshold are you using? Is that like how are you determining that threshold?
So here we consider the IOU larger than 0.03. If the IOU larger than 0.03, I will consider this a reliable object detectors. But there's a little bit ambiguous threshold. We try different threshold and evaluate how this is sensitive to the interpretability. But if we fix this threshold and use the same threshold for all the network, then it's comparable across different architectures. So here we further compare the different architectures. So we run network dissection on AlexNet, VGG, GoogleNet, RedNet, train down ImageNet and places. So here I will show you some object detectors across all the different architectures. So here is the house detector at the AlexNet, house detector at the VGG, house detector at GoogleNet, house detector at the RedNet. So you can see the IOU of the house detectors keep increase when we use much deeper network. So the house detector in GoogleNet and RedNet can detect more compact house compared to the house detector in AlexNet that only detect parts of the house.
Excuse
So-
me, could you please explain again, how do you obtain those images? How do you decide which part is black and which part is the actual receptor?
Oh, okay. So after we get the top activated images, because for each unit, we will generate a feature map. Let's say it's 14 by 14 feature map. Then we binarize the feature map, then upsample the feature map to the original image size. Then use the feature map to segment the whole image. Because if some units have high activation on special region, then it will segment the image region out. Does that answer your question?
But there is some arbitrary decision about the threshold, right?
Yeah, there's some threshold there. Okay. Then if you put a loose threshold, then you get a larger larger segmentation. If you put a smaller threshold, then it will get you pretty tight segmentation. But we use the same threshold across all the different architectures. That makes the result comparable across different networks.
Did I hear you say it was a 14 by 14?
Yeah, at some layers.
That's the size of Conf5? Is that
Yeah, Quantify is it's 14 by 14. Yeah.
So how come it's not blocking? I guess I would expect if it was
So we do bilinear upsample. So there's some Gaussian smooth on the feature.
smoothing.
Yeah. Let's start. So here is the airplane detector in VGG, GoogleNet, and RedNet. So you can see the airplane detector in GoogleNet and RedNet can detect more compact airplanes. Even the airplane detector in RedNet can handle the change of scales or some occlusion cases. The person standing in front of the airplane still can detect them. So here's some statistics. So here we can evaluate all the different networks and plot their unique object detectors and compare their interpretability. So here it shows that when we use deeper network, there are more interpretable unique detectors emerge inside network. So here the plot, we don't normalize by the total number of units. It's just a number of unique concepts across all the networks. You can see when we have deeper networks like RedNet, there are more object detector emerge. Also, there are more object detector emerge in the network trained on places for scene recognition compared to the network trained on ImageNet for object classification. So we can further use this to analyze some interesting phenomena inside the network. Previously, I showed you that a lot of object detector emerge inside the real tree network. But what's happening during the training process? So here I will show you the animation, the horizontal axis, the training iteration, the vertical axis, the number of unique detectors. So you can see as you train the network, as the training iteration goes up, there are more and more number of unique detectors emerging inside the network. It's correlated with the accuracy on the validation set. So I guess this is one, when you train the network, you monitor the validation loss. So you can see the number of unique detectors actually correlated with the accuracy on the validation set. Then therefore, you can use interpretability as a metric to monitor or debug your training process. Also, we apply this to analyze the transfer learning. So transfer learning is a very common scenario. So you have a pre-trained network, let's say you train on ImageNet, then you fine-tuning on your targeted data set. So, but what is happening to the individual unit during the transfer learning process? So we have done some experiment on the transfer learning. So let's say we have a pre-trained model on ImageNet, then we fine-tuning this to places. So here is one unit. So at the beginning of the fine-tuning, this unit that the ImageNet pre-trained model is detecting a dog. So it's a dog detector. Then we fine-tuning the whole network to places. So let's see how this unit change from one data source to another data source. So here is the concept before fine-tuning. So you can see before fine-tuning detecting the dog, so after we're fine-tuning the whole network to places, so those dog detectors mutate it into a waterfall detector. So let's do the other way around. Right now we have a waterfall detector. Right now we have a first have a pre-trained model on places, and we fine-tune into ImageNet. So how many of you think this will mutate back as a dog detectors? One. Okay. So let's see. Gradually change this concept. So the mutate come back to a dog detector because there's so many dog categories in ImageNet. So those network need to expand their capacity to encode different attributes of the dog. So it's mutated back as a dog detector. But this dog is a little bit different to the previous dog. But you can see compare the attribute and the concept. Although they are different, but they share some low-level similarities. They're detecting the white and black stripes. That's why they can, and those features can be reused to detect similar patterns. So here another my favorite example. So at the beginning in this unit detecting the stripes. Can anyone have a guess on which concept it will turn into?
Zero.
Okay, let's see how this will change into. Gradually change, mutate. So after fine-tuning, this unit change into a dog ear detectors. So you can see, compare the concept before fine-tuning, you can see those two patterns share such geometric similarities. That's why this feature can be reused, because they share such geometric similarities and the feature can be reused to detect those dog ears. Because there are so many dog categories here, those units need to encode the different dog attributes to better classify the dog categories. So previous work I already showed you that there are a lot of interpretable units emerge inside the network. Right now I have the question, how does emerge detectors relevant to the final prediction? It's giving this input image, give you the prediction as cafeteria. So why is prediction and how important are the interpretable units relevant to the final prediction? Because I guess most of you only care about final prediction. You want to get a better accuracy on the validation set or testing set. So you don't care about what learning inside. So let's see how this internal representation relevant to the final prediction. So last year, or not last year, 2 years ago, so we proposed a technique called the class activation mapping. So it's a technique to explain the predictions of deep neural network. So let's see, for the two image, the places common give me the prediction. The first one is the conference center. The second one give me the prediction of the indoor booth. So this class activation mapping can generate a heat map. So let's say for the first image, it can generate a heat map to highlight the microphone region, the most informative regions for the conference center prediction. For the second prediction, the indoor booth can highlight the poster board is the most informative regions for the prediction. So the technique can generate a heat map to highlight the most informative regions. So that can give you some sense why this image is classified into some categories. It will also help you debug the decision making of the network. So how this technique work? So here is the standard network, classification network, giving input image, the many convolution layers. So right now we want to build a connection between the final prediction, the class probability YC, and the unit activation map. So here, let's say we want to build a connection between the last convolution and the class probability. So between the two layers, so there is a layer called global average pooling layer. So this layer is doing that they average the feature activations at each channels and generate scalar value, then there is logistic regression after that, and give you the prediction. So because of the linear relationships, so I provide this only equations in the whole talk. So we have this logistic regressions. So this is a global average pooled values, then the logistic regression weights. Let's see here the logistic regression weight, then get the probability. So because of this linear relations, we actually can put the WK, the logistic regression weight, inside the inner summation. Then this equation becomes WKC multiplied the feature map. So this inner summation actually have very nice geometric meanings. So more like we have the W1 here, then we multiply the feature map of unit 1, then plus the W2 multiply the feature map of unit 2, and gradually sum them up, then get this weighted sum feature map. So give a name to this weighted feature map as a class activation map. This map is actually spatial visualization of the predicted value. Because you can imagine if we sum up this class activation map, it's more like we sum up so the height and the weight, then we get this, it's proportional to the predicted numbers. So this class activation map gives us a very nice visualization, which image region in most activity regions. So here is an example. So for this image, the places component give me the top 3 prediction. The first one is dome, the second is palace, and the church. So for each one of the prediction, I can generate heat map. So this is a heat map for the first prediction, and the prediction, the heat map for the second palace highlights this bottom regions, dome highlights dome regions. So for the church, is trying to combine the 2 regions, trying to combine the top region and bottom regions, generate this heat map. So the heat map gives us intuition which region is the most important region for the prediction. So we further evaluate this heat map for weakly supervised localization tasks. So this is a scenario that we only have classification networks, and how can we use a classification network for localization? So for the 2 input image, we can generate a prediction, and we can use a technique to generate heat map. Now we don't need a bounding box. We don't need to train with bounding box. Now, because we can, from the heat map, we can generate a bounding box and use the bounding box to localize the object. So this is why it's called weakly supervised localization, which means we don't train with bounding box annotation. We just use a classification network for localization without training with any bounding box annotation. So we get some numbers, so we compare with previous weakly supervised method. So our method outperformed with large margins. It's also getting closer to those fully supervised methods. So the AlexNet, they train with bounding box annotation. We get getting close, only 3% lower than the supervised method. It's more like we get localization for free out of some classification network. So we can further use this technique to explain the failure case. It's always interesting to see how this network make mistake. So let's see here is the one input image. So I took these photos when I visited a friend during the Christmas in my friend's house. So taking this photo, so I throw into the network. The network give me the prediction a sushi bar. So why this sushi bar? It doesn't make sense. So why that? So I throw this image into the network and generate heat map. It actually highlights the person standing in front of the kitchen island as the important regions. Also highlights the wooden stool as an important object. So you can imagine a sushi bar is actually always a chief standing in front of the wooden tables making the sushis. To make such mistakes, so you can see this network nerd those BIOS inside the data and give you such wrong prediction. So here's another photo. It's just a very boring person, probably a graduate student, sitting on the floor. So I threw this image. They give me the prediction at the martial arts gym. So totally have no idea why this martial arts gym. So can anyone have a guess on why this martial arts gym?
Bare feet?
Yeah, it's indeed the case. It actually highlights the bare feet are the most informative regions for the prediction martial arts gym, because in martial arts gym you will not wear your shoes. So you can see this technique can give you some sense why this network give you such prediction. So we further apply this technique to analyze the failure case in video. So we take a network trained on ImageNet, and then for each one the video frame, we generate the top 1 prediction. So here is the top 1 prediction, and we generate a heat map. So you can see the tension of the network keeps shifting over the frames. They make a lot of mistakes. Windows screen, they give the this one, the mountain bike. So this one is funny. Space, limousine, W zooming. Finally getting correct. That's speedboat. So you can see from this visualization, the network already have such implicit attention. You don't have to use those attention model written a lot of attention models. But there's already explicit attention inside the network. You just expose this attention, and you can visualize what this network is doing. So from this, we can see here are three failure cases. So for the first one, predicted park bench. Second one, predicted present. Third one, aircraft carrier. So why is that we generate heat map? So this heat map tell us that it's actually the network mistake the staircase as the park bench. Second one, they're actually seeing those buildings as background with a lot of windows as background. Also, this relating patterns and mistake this as present. Also for the aircraft carrier, because the speedboat is very far away, so it cannot clearly see the speedboat, such make the wrong prediction. So here we release all the code at the project page, so again you can download and play with this visualization and give you the intuition why this network give you the prediction. So here we have some work to analyze the importance of the individual units. So here is a recent paper from DeepMind. So DeepMind, they try to analyze how important the interpretable units. So they actually conduct some ablation experiments. So basically they remove one unit and then observe how the ablation affects the final prediction. So basically for this network, then they get the accuracy on the validation set at the 85%. Then they remove one unit, then the performance drop to 80%. Then you can see the unit importance is 5%. So this can give us some numbers to measure the importance of the units to the final prediction. So they have a scenario that we can either remove the units easy to interpret. So those are units like cat units, and we can remove them and see how it damages to the prediction. Or we can either remove those confusion units, those are units don't have clear meanings, those are less interpretable units, and see how they affect the final prediction. Then they can analyze how the interpretability relevant to the unit importance for the classification task. So they actually get a pretty interesting result. So here for each dot is a unit. Then they remove the unit. Then the horizontal axis is the interpretability. So they use class selectivity and the interpretability. Like after you remove this unit, how? So see actually the vertical axis is the importance of the unit. So you use loss on the validation set to measure the importance. If you remove this unit, then the drop in the validation set, then use that number as a measure for the unit importance. So for the interpretability, they use class selectivity as a metric for interpretability. Basically, they measure how this unit is selective to some classes. So from this plot, you can see there are actually pretty weak correlation between the two, which means no matter how interpretable the unit is, it not contribute more to the final prediction. This result actually upset me because I spent so much effort on treating this topic because we want to make the network more interpretable so we can improve the performance. Actually, they get the opposite results because no matter how interpretable unit is, the performance is just the same. So I went back and rerun all the experiments. So it turned out it's indeed the case. But I already have my shade to defend, so this is fine for now. However, I found something interesting. So actually I found out, so that's their conclusion, that the cat unit may be more interpretable, but they are not more important. So actually I found, so there is there implication. You see that the method for understanding the neural network based on analyzing highly selective units may be misleading. So you see, those line of my research is misleading. So I rerun all the experiments. So actually I found out, although the damage to the overall accuracy is trivial, but the damage to the class accuracy is actually significant. So here is one example. So here's one unit. Here is the top activated images from those visualization. We can see this unit is selective to the bed. So if we remove this unit, then compute the job on every one of the class Now we can sort all the class by their job in class accuracy. So here is the sorted class accuracy. So we can see for some of the classes, such as use hostel, bad rule, bad champer, children's rule, the damage is very significant. So here are some image samples from those top 3 damaged classes. So you can see by removing these units, the net damage to the use hostel is 24%, damage to the battery is 50%, and damage to the bad champer is 30%. So from this result, you can see that actually it's very important. Those individual units is very important to the subset of classes. So more interesting, that some units actually benefit from this unit removal. It's more like if you remove this unit, their accuracy will improve a little bit. That some images, like 4 or 5 images, will be classified correctly by removing the unit. So here is another unit. So if we remove this unit, so from this unit is selective to the wheels, so we can rank the class accuracy. Here are the image samples from the top 3 damaged class. So you can see the model T, the damage is 40%, and the bicycle beautiful 2 is 30%, the unicycle is 50%. So you can see if we remove this unit, then this network cannot accurately classify those categories relevant to the wheels. So we can further use compute the sorted result for each one of the units. Right now we use max class accuracy job as a metric to measure how important this is to some specific class. So basically we take the max class accuracy job as a metric for each one of the units and sort all the units at 1 layers based on their max class accuracy job. So here is a sorted plot. So you can see for some of the units, the damage is more than 50%. But for some of the unit, the job is 10%, the max class accuracy job. So we also, for each one unit, we plot the overall accuracy job. Because for overall accuracy job, no matter how interpretable units, the damage is almost the same. This is what DeepMind people doing again. So they just ignore to analyzing the damage to the class accuracy. They're only looking at the job in the validation set. So it's more like overall accuracy. So you can see here, I show those units with the largest max class accuracy job. So those are units very selective to some objects. So here I've also plotted some units with the least max class accuracy job. Those are units like sensitive to some attributes or some textures. So those textures could be shared across different categories. So those are less important to those individual units or individual classes. So the next slide is a correlation. So this is a correlation. The horizontal axis is a class selectivity. This is what DeepMind people use as an interpretability. The vertical axis is the overall accuracy job. So you can see the correlation is pretty weak. It's only 0.3. So this is just we reproduce DeepMind people's result. But here we further compute the correlation between the class selectivity and the max class accuracy job. So you can see there are significant correlations. The minus 0.2 correlations. So this correlation actually very significant, which means this units actually very important to some subset of classes. So you can see recognizing some individual classes, the information is actually coded on a subset of units. So we further conduct some greedy removal experiments. So we select one class, then greedy remove the unit that maximize the damage to the class. So we can see after we remove about 10 or 15 units, the performance for that individual class already dropped below 10%, which means the information about some class encoded by a very limited subset of units. So those units plays a very important roles to recognize the categories. So we further evaluate how the different training regularizers such as bachelor or dropouts affects representations. Because those are the training regularizer commonly used to prevent overfitting of the models. Here we have some experiment showing that the training regularizer actually affects the interpretability. So we have 3 networks. The first one is a baseline network. So here is the curve, the sorted max class accuracy job. So another network is a network, baseline network with batch normalization. So we put batch normalization on each one of the convolution layers. So you can see the batch normalization layer actually reduces the information content at each individual unit, reduces max class accuracy drop curve. So another network is a baseline with channel dropouts. So we put this channel dropout as a Quantify layers. So this channel dropout is a little bit different to the normal dropout. So each time we drop 50% of the channels. So which means at each training iterations, 50% of the units you randomly drop out over the training. So this training regularizer actually greatly shuffle the information content at each individual unit. You can see this curve greatly getting closer to the x-axis, which means there are much less class information content at each individual unit. So this training regulator actually forces that we're doing the distributed coding. Try to encode each one of the categories across all the units rather than some individual units.
But are their accuracies comparable? So with the different regularization?
So this, the batch norm and the baseline getting pretty similar performance. The channel dropout about 2% lower, but it's still pretty close. So you can see previously training regulator, the batch norm and dropout is only proposed for preventing the overfitting issue. But you can imagine in the future work there could be some regulator that can encourage the interpretability of the network and try to make the network and the internal representation more interpretable. This is also one of the ongoing projects we have. So from this result, you can see the dropout greatly scatters class information across all the units. Also, there may be some trade-off along the performance, interpretability, and the robustness. Right. So some latest work, like we have some ECCV work that we can use the knowledge concept basis to generate the explanation for the prediction. So for this image, to generate heat map using the class activation map, but this heat map doesn't tell you what object is highlighted. So we have some latest work that can further decode the internal states and generate those by project this heat map on several interpretable bases. Then we can generate some language explanations. So because for each one of the bases, we have some annotations. Then we can generate some language explanation for the predictions. So also have some ongoing work to interpret the medical models. So here is a network trained for the mammogram classification in the breast cancer prediction. So we can visualize the internal units. It turns out a lot of internal units are detecting those diseased tissues. Some units are detecting those masses. Some units are detecting the vascular calcification. Then we can further use a unit activation to build some explanation for the medical decision makings. Because in healthcare or medical imaging, the explanation is very important. You can generate some explanations and make the patients more friendly to the AI models, medical models. Okay, so here's the conclusion. So I hope after the talk I can convince you the interpretability is a very important topic. We want to work towards more interpretable representation learning with more interpretable deep learning models. So hopefully those deep learning models can be used to those real scenarios such as autonomous driving, healthcare application, or whole robots. So lastly, we want to correct this alchemy of deep learning into a chemistry of deep learning by putting the interpretability insight. I would like to thank all my collaborators at MIT and other institutes. Yeah, that's the end of my talk. Thank you for your attention.
Thank you very much. I think before we go for the question round, could you do me a favor and press the upper button on the light, maybe that we get a little bit. Thank you very much. Also, I want to thank some people I forgot at the beginning. I want to thank Lana and BC who helped setting up the room. Thanks, John, for filming, and thank you for coming along with the talk. Let's go for the question round.
So I was just wondering if it's possible to use pixel level data for each image. along with your techniques to improve the accuracy of your results?
Yeah, actually, people using the heat map technique to improve the training accuracy, because it can help you identify which region is the important region. Then you can, during the data training process, you can crop the regions and feed those regions back into the training process and try to correct the prediction of the network.
So I'm wondering if you train multiple models using the same data, does the same unit does the same thing or similar thing, or do you find any interesting patterns?
Yeah, that's a very interesting question. So we actually rerun the experiment. So in our general extension of network dissection, so we found out, so about 80% of the units, they keep showing up. So about 20%, it maybe depends on the initialization, or because also the training process is a non-convex optimization, so maybe some local minimal, so they are not so frequently showing up. So about 70 to 80% of the units keep showing up.
I'm curious, do you know of any tools that are on the horizon for development, or perhaps libraries like TensorFlow, Keras, PyTorch that have this in their roadmap?
What do you mean by in the roadmap? So here we release all the libraries in PyTorch or Cafe, so you can download and play with them.
Sure.
So I think it's already get I think 400 stars on our GitHub.
Sure.
So a lot of people using this technique in the research. So you can download them and play them. I think the class activation map also, I think it's already implemented in TensorFlow.
Okay.
So you can use out of box.
Okay, thank you.
So thanks again for the talk, very interesting stuff. So you showed us that non-interpretable units also are pretty important. So do you have any sense of why they're important? What do they do?
Okay, so that's a very interesting question. So here we observe 1/3 to one third of units have a very clear meanings. So another half, they may not previously align with the concept in our dictionary, because our dictionary have 1,200 concepts. So some of the units we found out, they really like a quarter of the rule, like we don't have a name, a human name for those concepts. So they may be detecting those kind of concepts. Another thing is that some of the unit, maybe they do the distributed coding. They jointly represent some patterns. So therefore, their IOU will be lower than our threshold. So they identify as a confusing unit in our case. But here we are improving our dictionary by including more concepts. So we also try to train the network to make them, each individual unit, more interpretable, more aligned with the concept in our dictionary.
Maybe last question.
Okay, just one quick thing. Like when you choose the concept, you could potentially choose from an infinite pool of concepts. You could choose whatever you can think of, and maybe some concepts might be more representative than others. So, is there a way of finding, I don't know, a ranking or an ideal pipeline to say, well, you don't have to look to 1,300 concepts. You can just look at these 10 first.
So that's a good question. I guess if you want to do that quantitatively, you have to still evaluate over all the 1,200, then rank those concepts by their numbers if you want to get the most confident concept. Yes, what we are doing for the network dissection. But some of the concept is out of our dictionary, then we cannot identify the concept.
If you can shout your question, maybe last one, just to stay a little bit in time.
Okay. Thank you, Bolei. I have a question about this is a very interesting topic, and it's there. Does this your research shed any light on how our human brain neurons to interpret our vision, or from the opposite direction, how brain neurons should give you any insight into your research?
Yeah, that's a very interesting question. It's also a very broad question. So one of my collaborators, Audrey Oliva, so with MIT and IBM executive director. So her background is on cognition and neuroscience. So we actually have some ongoing work, try to do brain dissection, try to use this technique to identify those units that specialize to recognize some object, discrete object. So we are use fMRI to just put the human subject inside and throw the image to the human subject, and then record their activation. Then we can associate the image regions to the brain regions, and then identify those regions specialized to recognize some object. But I think there are some correlations between the two.
There's also, if I can step in there, there's also a whole research branch devoted to this, which is called Neuro-Inspired AI. And one of the people who's in the forefront of that, David Cox, he was at Harvard before, just joined the lab here as well. So there's some work in this direction. I can definitely send some pointers.
Thank you.
Yeah. Okay, thank you very much again. If you have individual questions, I think you are here for a couple of minutes. Besides that, hope to see you in August. We are planning for late August something in Boston. Not on the Cambridge site this time, since it's called Boston Machine Learning Meetup. Cambridge Machine Learning Meetup. Okay, thanks a lot, and see you soon. Bye.